free frames. So what are free frames? So before allocation, the memory will have the free frames that are available for allocation. So free frame list is 14, 13, 18, 20, and 15. And new process page 0, 1, 2, 3 needs to be stored. So after allocation, you can see that page 0 is stored in the first free frame list, that is 14. So in 14, you can see that page 0 is stored. And similarly, in page 1, frame 13 is the next free list, free in the free frame list. So in 13th frame, you can see that page 1 is loaded. And in the second page is loaded in 18th frame. Why? Because in free frame list after 13, 18 is the next free frames. So that why in 18th frame you can see that page 2 is loaded. And similarly, when you go for third page, it is stored in 20th free frame. So why? Because the 20th is the free frame, which is available after 18th frame. So in 20, third page is stored. So the remaining after allocation, what is the remaining free frame list? You can see that only 15 is the remaining free frame list. So whenever a new process comes, the 15 will be the frame number which will be allocated for that new process. So this is how allocation happens, and the free frame list is maintained by the operating system. So implementation of page table. So what is page table? So page table is kept in main memory. So you can see this in this diagram. This is the page table 0, 1, 2, 3, and there are 14, 13, 18, 20 is the frame number. So this is how the page table look like, page number, and correspondingly its frame number. So how it is implemented? So it is the page table is kept in the main memory. So inside main memory, where your particular page table is stored. So imagine that for 5 process, what we have seen already in the diagram, the page table is maintained. So similarly, after some time, some more new process arise. So those process frame numbers will be kept in another page table. So a memory will have more than one page table. So you need to know where your particular page table is stored in the memory, the address where it is stored. So for that, you are going to use a base register, that is page table base register, which contains the static address of your page table. And page table length register is going to indicate the size of the page table. So when you see the previous diagram, the size of the page table is 4. So page 0, 1, 2, and 3. So the size of the page table is 4. Say for example, your page table base register address is 4000. So your length of the page is 4. So how many spaces it is going to take? 4000 plus 4. So the last page details will be stored in 4004. So the size of the page table is indicated by the page table length register, and the base address of the page table is indicated by the page table base register. So in this scheme, every data or instruction access requires two memory access. So first you need to take the page table, then only you can search for your particular data or instruction frame number in the physical address, because if the page table you are not actually stored, means you cannot able to retrieve your data and instructions memory space. So therefore, the first memory access is going to be for the page table, and once you retrieve the page table from the memory, the second memory access is going to be for the particular data or instruction you want. The two memory access problem can be solved by the use of a special fast look hardware catch, which is called as the associative memory or transaction look aside buffers. Okay. So the two memory access problem, that is one for the page table and one for the data or instructions, can be replaced by this associative memory or translation look aside buffers. So you can see a diagram for this. So associative memory is the parallel search. So page number and frame number. So if A dash is an associative register, get frame number out. Otherwise, get frame number from page table in memory. So what is this associative memory is the recently seen page pages and its frame number. That is the address of the physical memory, which is called as a frame number. So that is stored in this associative memory. So it is otherwise called as a cache memory. So the recent looks of the page number and frame number will be stored in the associative memory. So whenever you want to give a search, so if it is already seen pages or frames, then you can directly go into associative memory instead of going for the search of the page table in the memory. So if you find that particular A dash in the page number of the associative memory, go or take the corresponding frame number from the associative memory and you can get your data or instruction. But that is the A double dash. If you are not able to get the or retrieve the page number what you are searching for in the associative memory, which means that particular page is not recently viewed. So therefore, that needs to be checked only with the page table. So you will go for the accessing of the page table from the memory. Then you can access your page, which is not available in the associative memory. And paging hardware with this translation look aside buffer. So what is paging hardware is the CPU will give you a logical address along with the offset, that is D. So that page number what you want to search P, that will be checked in the transaction look aside buffer, that is going to be the associative memory. If it finds that particular page number in the associative memory, then it is called as a TLB hit. Okay, so when it is a TLB hit, then the frame number will be taken directly from the associative memory table, that is TLB, and the offset will be added. So you will get your corresponding physical address. And if it is a TLB miss, what is TLB miss is you cannot find the page number and frame number in the associative memory, that is your page is not recently viewed. So then it is a TLB miss. Then you will go for the search of the page table in the physical memory and you will find the frame number of the physical memory, that is F, and you will add the offset. So you will get a corresponding physical address in the physical memory. So this is how, with the help of associative memory, you can identify the frame number for the corresponding page number. And what is memory protection? Memory protection implemented by associating protection bit. So you need a protection bit for each frame. Why? Because you have to tell the corresponding search as whether it is a valid search or invalid search. If the particular page is found, then it is a valid search. If the page is not in the process, then you can say that it is an invalid page. Say, for example, you have a 10 lines of code for a process and you are searching for the 11th line. So the 11th page is not available in the page table, which means that it is the invalid page you are searching. So if it is an invalid page, you don't have the corresponding frame number, so you cannot going to retrieve the particular page number. So you are giving a protection bit. That bit will have either 0 or 1. If it is a valid page, it is going to have the 1 as valid bit and 0 if it is not able to find that particular page what the user is searching. It will be 0 for invalid bit. So that is given as a diagrammatic representation here. So you can see that page 0, 1, 2, 3, 4, 5 and the corresponding frame number in the page table. And along with the page number and the frame number, you can also able to see the valid or invalid bit. If it is a valid bit, it has been represented as V and it has been represented as I, which means either 1 or 0. So when a particular person search for a page number of 1, so it is available, the corresponding frame is available for page 1. Why? You can see that the valid bit is V here. That is, this particular page still resides in memory. But the person is searching for a page of 6. So the frame number is 0. he can easily identify that particular page is invalid to search because it is not available in the memory with the invalid bit, that is I. So the searching time will be reduced for the user and he can identify that particular page is available in the frame or not. So page table, you have a structure for page table, how to use your page table or how to store your page number and frame number in the page table. So that is based on three types. One is hierarchical paging, hashed page tables, and inverted page tables. What are hierarchical page tables? The logical address space will be divided into multiple page tables. So as we have seen in the previous example, you in a particular page, you are storing four values, that is four data A, B, C, D. So that is the logical address space. You need to divide it into multiple page tables. A simple technique is a two-level page table. So if you have more number of pages available for a particular search, then you have to search in two indexes. Say for example, you have a book which contains two indexes. That is, the main index is going to be for each chapter. Uh, that is the main index. So you have five chapters. Number one chapter is available in a page of one, and number two chapter is available in the page of 100, which means chapter one, which contains 100 pages of details. So if you want to search in that particular 100 pages of details, you need to have a sub page table which contains only the details about the chapter 1. So if you want to access the 98th page of chapter 1, so that will be available in the second split up page table. That is, the 98th page will be stored in the corresponding 98th page only. So therefore, the physical address is going to be for this 98 logical address is again 98. So therefore, you can easily identify the 98th page of chapter 1. So you can have any number of levels of page table according to your request, because if you have a more large number of page tables, it is not easy for the memory to or the CPU to search in the memory. So it becomes a tedious process. In order to avoid that, you are going to split up that page table into different levels, which we are going to see now. So this is an example for the two-level paging example. So you can see that in the diagram, the page number and the page offset is D. So therefore, PI, P1 and P2 is the two level of page which is divided. P1, a page number consisting of 20 bits, a page offset consisting of 12 bits. So you can divide this particular page into 10 plus 10 only, or else you can divide it as 12 plus 8 also. So according to your necessity, you can divide the page number, but the offset page is actually 12 bits only for a logical address. Since the page table is page, the page number is further divided into 10-bit page number or a 10-bit page offset. So even if you want totally 20 bits or if you want only 10 bit of the page number, that is one division, instead of two levels, you are going to have one level, means then you can use only one page number of 10 bit and 10 bit of page offset, where PI is an index into the outer page table. So why they have given PI and P2 as P2 is the direct access of the 10 bits of data, and PI is the outer page table index, and P2 is going to be the displacement within the page of the outer page table. So that means the PI is the total pages, the total number of pages, maybe anything, some thousands, and P2 is the page from the 1000 what you're going to search for. So that is available in this 10 bits of P2. So this is a two-level page table scheme. You can say that outer page table contains data about the inner page table. So inner page table contains the data about the frame numbers, which has been given in this diagram. So you can see that outer page table is connected to each and every page table. So the first one is 1 to 500 lines of page numbers will be connected with the outer page table of only one one page. So one page of outer page table contains the inner pages of 1 to 500 lines. And similarly, it goes on. You can divide it into any types. So this 1 to 500 is further, you can search it in the memory, and it is stored in a particular number starting from 1 to 100. So totally it is going to have that is 100th page. And when you go for 500 lines means it is going to be stored in the 500th page. The page 1 will be stored in the frame number 1, and the page 500 will be stored in the page number 500. Address translation scheme. So logical address P1, P2 and D. So P1 is the outer page table from where you can go into the inner page table, that is P2, and with the offset when you add, you can directly go into the main memory to access that particular page. What is hashed page tables? So it is common in address spaces which is greater than 32 bits. The virtual page number is hashed into a page table. This page table contains a chain of elements hashing to the same location. So virtual page numbers are compared in this chain, searching for a match. If a match is found, the corresponding physical frame is taken out for and give it to the and has been given to the user for their accessing of data. So the hashed page table, any hash function can be applied, and with that hash function, the logical address, that is page number, will be taken and the offset D is given. So this particular hash function is applied to the page number, the same hash function which is used at the time of storage of this particular page P. So the same hash function could be anything. It's of prime number type of function, or it could be some Armstrong number finding function. So whatever hash function formulas you can have, so that same function is applied when you are going to take out the data or accessing the page. The particular hash function is applied to the hash table. And we have got that Q and S, the data, that is the frames where your data can be stored. So this is a continuous data. So you can see that in the second page, you can see that R is given. So that R is the actual data you want. So from that R, you can add the offset value D, so that you're going to get your physical address. It's like a linked list. The storage happens in the hashed page table as a linked list. Q is the previous data and the next data is P, and R is the next address is P, and Q is the previous address. So S is the data here, and in the next thing, P is the physical address of the previous data, that is yes, and R is the data, and the next column for R is for the next address, next data address. So it is like a linked list, or it is a chained list. So when you pass through all the chain values, you can get your particular data. So without passing into that addresses of addresses of next value, that is stored in the next of the data. So you have 3 bits for this. One is the previous address, that is Q or P, and the data in between, that is S or R, and the address or data, and the final bit is for the next address of the next values address. So totally you have 3 bits in the chained value. It's a doubly linked list. And what is inverted page table? One entry for each real page of memory. So entry consists of the virtual address of the page stored in that real memory location. So with the information about the process that owns that page, the decreases memory needed to store each page table, but increases time needed to search the table when a page reference occurs. Use hash table to limit the search to one or at most a few page table entries. So you can see this inverted page table architecture. You are giving an ID for the a page, that is PID, and you are going to search with that PID in the page table so that you will get a page number corresponding to that PID. And with that displacement value I, you're going to add the address of I with the displacement value D so that you will get the physical address in the physical memory. So each page will be given with the physical, that is page ID. The page table also contains the details of the page ID and also the page number. And what is shared pages? So you can have a shared code or a private code. What is shared code is, if more number of people is going to access the same data, the same code is going to be appear in the memory in one place. The same place will be accessed by more number of people, those who want the same data. And private code is a separate copy of the code will be given to more number of users. So if 100 users request a particular data in the memory, then that is a, if it is a private code, then each copy of the code can be shared to the each and every user. So one copy of read only, that is re-entrant code shared among the process, that is text editors, compilers, Windows systems. If more number of people in an internet, in a network connection request the text editor, for all the people, the text editor will be stored in the same place in the server, and the space where the text editor is stored is shared to all multiple users. So the shared code must appear in same location in the logical address space of all process. The private code is each process keeps a separate copy of the code and data. The pages for the private code and data can appear anywhere in the logical address space. Logical address space is the user address space. So you can see an example for this shared pages. So in process P1, you have 3 editors and data 1. So you can see the corresponding page table for P1, that is 3461, which is the frame address. So you can see that 3461 where editor 1 in 3, editor 2 in 4, editor 3 in 6, and data 1 in 1 frame. Okay. And when you go for the process P2, the editor 1, 2, 3 are the same and data 2 is the only difference. So when you see the page tables for P2, you can identify that the editor where it is already stored, that is 3, 4, and 6 is the frame number. The same frame number is used for the process P2 also. So that means the editor in that particular frame is shared by 3 processes here. Even when you go for the process P3, you can see that editor 1, 2, 3 are the same and data 3 is different. And 3, 4, 6 is the same frame address where the editor is stored in the physical memory is given in the page table. So this is how shared pages are accessed by memory. And the next one is segmentation. So the memory management scheme, apart from paging, you also have a segmentation part. So each logical unit of your program will be divided into segments, and these segments can be collectively called as a program. So a segment is a logical unit. So you can see that main program. Inside that, you can have a procedure or function or a method. Some objects you can have local variables, global variables, common blocks, stack, symbol, table, arrays. So everything inside your program can be divided as segments. The main program is a segment. Procedure 1 is a segment, procedure 2. So whatever number of procedures you use, everything bears a separate segment. So user view of a program. So the logical address space which contains the segments of your program. So you can see that square root is a function used in your program. It is a separate segment. And main program is a separate segment. Symbol, table, and stack used in your program will be a separate segment. Subroutine, which is called as a function, which does not return anything, then that subroutine is also a separate segment. So logical view of segmentation. So how the memory will store this segmented data. So you in user space you have given 1, 2, 3, 4 as segments, 4 segments. The physical memory in the physical memory space also you can see that the spaces where your segments are stored. So in different frames the segments are stored here. So the segmentation architecture also contains two addresses. One is the base address, another one is the limit address. Base address contains the starting physical address of the where your segment resides in memory, and limiter specifies the length of the segment. So two tuple will be used in segmentation architecture. One is the segment number and the offset. And you also have a segment table for mapping the physical address and the logical address of the segments. And you also use two register as you have used in the paging. Segment table base register and segment table length register. Segment table base register is the starting address of your segment, and segment table length register is for each segment. What is the length of the segment will be stored in the segment table length register. So the segment number is represented as S. The accessing of the segment becomes illegal if the S is less than the STLR. STLR is nothing but the length of the register. So imagine that a segment contains of 6 lines of code means, and you are accessing for a the fourth segment contains 6 lines of code, and you are trying to access the segment number that is 5. So which is not available because you have inside the program only 4 segments. So each segment contains some 6 lines of code. So, but you're trying to access the segment number 5, which is not the actual length of the register. So you imagine that for each segment, 6 frames are allocated. So therefore, 4 segments means 6 4 24 frames are allocated, but you are trying to access the fifth segment, third data. So third line. So what happens is if you had already the 30 frame numbers for the segment, fifth segment, the user can access that particular number for the fifth segment. But if he is trying to access greater than 30, in this case, you have only 4 segments. So greater than 24, which means the segment number is not available. The length register is 24 only. And the segment number you are giving us 5. So which is not, which is less than the segment table length register, which means this accessing of that particular segment is illegal. And relocation is nothing but it happens in only in the dynamic way, and the corresponding relocation of the frames or pages will be stored in the segment table automatically once it is relocated. The code gets relocated inside the memory. Relocation is nothing but moving the code from one segment to another segment. And what is sharing? In the segmentation architecture, the segments can be shared. As you have shared the pages, in the similar way, the segments can also be shared, and the segment number address is going to be the same as like in the paging. The page number of that particular common data like editor 1, 2, 3 was 3, 4, 6. In the similar way, the segment number will be same. Only the address of the address of the segment is also the same in all the requisition of the user. So which means the segment number is shared between the user, and any type of allocation is possible, first fit and best fit, and not the worst fit. So even though you use the first fit and best fit, you will get an external fragmentation when you use the segmentation architecture, because the corresponding the segments or assigned some values. So if you have 24 lines, so totally 4 segments means it is allocated 30 that is 30K space, then it becomes 6 spaces which is wasted. So that six spaces are called as external fragmentation. So you have also the protection bit, that is validation bit for 0, that means illegal of accessing that particular segment. Read or write or execute privileges you can give for the segments which is not available for the pages or logical address space in the paging. So here a segment can be updated, a segment can be deleted, a line and segment can be deleted, or a complete segment can be deleted. So all type of privileges, whatever you want to give for the segment, you can give. It is completely applicable for all the lines in the segment, and the protection bit is associated with segments code sharing occurs at segment level. Here, no inside lines of the segment is shared. The complete segment will be shared. And since segments vary in length, memory allocation is a dynamic storage allocation problem, because one for one program, you may have a six segments. For one program, you may have some eight segments which cannot be predicted already, because each program is not of the same size, so you cannot predict it already. So therefore, dynamically it has to be allocated. Whenever the segments comes, it has to be allocated in the memory. And a segmentation example is shown in the following diagram. So this type of allocation is very tedious for the memory. So segmentation hardware is, again here CPU is given with the segment number S and the offset, that is the inside line which the user wants to access that particular segment, that is D. So when the value, the segment table, you have a limit and base register. What you are searching S is less than the segment table limit value, then it is the addressing error. Sorry, greater than limit value, it is an addressing error. But if it is less than the limit value, you can add the base register, base registers with the limit values that will be stored in the physical, that you can access with the physical memory. An example of segmentation given. So in the logical address space, you have so many segments, and subroutine is segment 0. When you go to the segment table, you can see that the limit is 1000 and the base is 1400, which means that number of lines in the subroutine is 1000. So from the 1400 base address, it is going to it is getting stored at the 2400 memory space. And when you go for the first segment, again the base value is 6300 and the number of lines is 400. Totally, it will take from 6300 to 6700 space. So this is how segmentation is allocated. Sharing of segments is also possible. In the logical memory process P2, you have two segments 0 and segment 1, and similarly in process P1, you have segment 0 and segment 1. Whereas the editor is that is the segment 0 is common for both the process. So when you see the segment register, you can see the base address of the editor is going to be 43,062. So you can see that same base address for both the process P1 and P2, and the limit address, that is the total number of lines in the editor is 25,286. When you add 43,062 plus 25,286, you will get the final address, that is 68,348, where the editor ends. So the same value is given in both process P1 and P2, because we are going to share the segment which is already stored in the 43,062 to 68,348 memory address. So that's why the same address is base address and limit value is given for the segments. The next topic we are going to see is virtual memory. So virtual memory, it's a separation of the user logical memory or from physical memory. So user logical memory is the address what the user gives, and the physical memory is the address where the actual data is stored in the memory. Only part of the program needs to be in memory for execution. So no need for the complete data to be in memory. Whenever needed, we can swap it and use it. Logical address space can therefore be much larger than physical address space, allow address spaces to be shared by several processes. It allows for more efficient process creation. So Virtual memory is nothing but an imaginary memory of the user logical memory. All process creation, sharing, and the overlay concept, everything is possible. What you have in actual memory access in virtual memory also. So this can be implemented. How you can create a virtual memory is you can use demand paging or demand segmentation for this virtual memory. So you can see a diagrammatic representation of the virtual memory that is larger than the physical memory. So the virtual memory is page 0 to page n you are having, and the physical memory, when you compare, it is very less. So you are storing those details in the backing store. So the physical memory cannot store the complete blocks which is available in the backing store in the physical memory, because the physical memory space is very less. So therefore, a memory mapping is needed in order to find the corresponding frame number of the the logical address, that is the page number. So that memory map is made, and if suppose that particular page is available in the physical memory, then it is shown to the user directly, or else it has to go into backing store and do the process of roll in, roll out, the swap in, swap out process. So whatever the page needed by the user will be swapped from the backing store into the physical memory, and the data is stored to the shown to the user. So this is how the virtual memory mapping with the physical memory happens. So page replacement. So what is page replacement is, in the previous diagram, I have shown that whenever needed, from the backing store, the pages are swapped inside and swapped out. So the swapping, so the concept is the swapping in and swapping out of which page, for rolling inside the pages which is needed by the user from the backing store to the memory. You need one page to be replaced or relocated. So that particular page replacing, how to find it, because you have so many pages in the memory. So which page is going to be the victim for the replacement? So that you need to find based on some conditions. We are going to see all those things. And use modify bit or dirty bit, it is called, to reduce the overhead of page transfers. Only modified pages are returned to disk. So every time, if or every time or a you're changing the pages, so that particular page will be um, marked with the help of this dirty bit, that this page is changed for this much of times. So what happens if a particular page is 100 times it has been swapped in and swapped out, and one of the pages not swapped in, it's only for 10 times it is swapped in and swapped out. So you can take for the next time, the victim of page replacement is the page which is swapped in, swapped out for 10 times, instead of this page which is swapped in, swapped out for 100 times. So so this type of overhead can be reduced with the help of this dirty bit. So you can see the number of times a bit has been transferred, and whether we can use those pages as a victim for the next transfer. So the page replacement completes separation between logical memory and physical memory. Large virtual memory can be provided on a smaller physical memory. If you have a smaller physical memory, you can use this virtual memory to store the pages. Instead of storing it in backing store and in physical memory, swapping in and swapping out, you can even use the normal, instead of normal memory, as it has only the small amount of memory, you can use the uh, that virtual memory for instead of this physical memory also. So this is the diagrammatic representation of the need for the page replacement. So you have logical memory for user 1 and user 2, and the corresponding page table for user 1 and user 2. So you can see the physical memory here, and also B and M block has been stored in the backing store device. So the in the logical memory, In the logical memory for user 1, load m is the command which is given. So when you that is inside the page, inside the page 1. So inside the page table, you can see the frames that is stored and the valid or invalid bit. So page 1 is stored in the frame of 4. So when you see the physical memory, load m is the command which is stored in the frame 4 that is available now. And when you go for logical memory for user 2, you can see that some bits are valid and some bits are not valid. So you can see the B is the page which you want to access, which is the page number is 1. And when you check the page number 1 in the page table for user 2, you cannot be able to see it because it's empty and the bit is I, which means accessing of B from the physical memory is not possible because it is not available. So therefore, it needs to check to the backing store. In the backing store, B is available. So therefore, what happens is the page needs to, some of the page needs to be replaced for storing the B page from the backing store into your physical memory. So once it is stored into physical memory, you can say that the user can access the address of the physical memory through the page table, because the page table will also be updated once the page is loaded from the backing store to the physical memory. So the B is the data which needs to be loaded into a particular memory space in the physical memory. And similarly, the load M is the command. The command contains the M page needs to be loaded. So both M page and the corresponding B page invalid is also, if it is needed, it needs to be loaded from the backing store only by choosing any one of the page in the physical memory as a victim. So this is how the page replacement occurs, because the memory space of the physical memory is very less. Memory size of the physical memory is very less. So therefore, it needs to be stored in backing store, and whenever needed, it needs to be getting out from the backing store and placed in physical memory. So this is the need for page replacement. So basic page replacement contains these steps. So find the location of the desired page on disk. And in step 2, find a free frame. If there is a free frame, use it. If there is a no free frame, use a page replacement algorithm to select a victim frame. So read the desired page into the newly free frame, update the page and also the frame table. So you can see this with the diagram. So in this diagram, you see the page table which contains frame 0, that is an invalid. So we cannot be able to use it, and frame F, which is a valid bit, which can be accessed. So what is the first step given? The first step for the page replacement is swap out the victim page. So victim page is F, because you have only one page, that is frame F. So the frame F is accessed, and that is going to be the victim page, because victim page can be selected based on some conditions. So this victim page is selected, the F is selected now. So therefore, this page needs to be replaced into backing store. So swap out from the physical memory to the backing store. That is your first step. And your second step is change the bit into invalid, because this victim page F is not now available. So therefore, F, which contains B bit, will be converted into I bit. And after this, the third step is swap in the desired page you want, so which is available in the backing store. And once you swapped in that page, so you have to again change the pages in the page table along with the bit also. Okay, so this is how you need to do the page replacement. So we have some algorithms to evaluate the page replacement. So we want a lowest page fault rate. So what is page fault is, if the if the page needed by the user is checked in the page table, and if it is not found, then it is a page fault. If there is no free space available to change, swap in the victim, and if there is no free space available for a new page to enter, then we can say it is a page fault. So the page fault rate may get increased if you find more number of pages which doesn't have the space to store in the physical memory. So therefore, our motive is to reduce the page fault rate. So whenever you get the page fault rate only, you are going to use the page replacement techniques. So when you use the page replacement technique, all the 4 steps to be followed, which is a tedious process for the memory. So where the frequent usage of this page replacement techniques will lower the execution or speed of the memory. So therefore, we need to avoid the page fault rate. So in order to lower the page fault rate, you are going to use algorithms. And so the pages for the reference string is being given. The pages given here is the reference string. So what you are going to check it in the memory. If that particular page 1 is not available, then it's a fault, page fault. If you have to do the page replacement. So if the 2 is available, then there is no page fault rate. So for each algorithm, a technique is going to be used in order to find the page fault rate. So whichever algorithm gives you the for this particular reference string gives you the lowest page fault rate, then that is going to be the best algorithm you have to use for the page reduction of the page fault rate. So this is the graph which is given for the page faults. So you can see in the x-axis number of frames and in the y-axis number of page faults. So you can see that whenever you increase the number of frames, the page fault gets reduced. So if you see the frame 4, the page fault is only 4. When you see frame 1, the page fault is 15, which means if you are having only one frame, the page fault is going to be 15. And if you are having some 6 frames, the page fault is going to be reduced to 4 or 2. So whenever number of frames increases, page faults get decreased. So this is the explanation for this graph. So the first algorithm we are going to see is the first in, first out algorithm, FIFO algorithm. So whichever page comes first, that will be the victim page for the next page to come inside. So that is the first in, first out. So the reference string is given here 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So in this example, you can see that 3 frames is there, only 3 frames are here. So the first time you are going to store the first reference string values 1, 2, 3, because the first time when you see the page table, you can say that empty page tables are going to be there because there is no pages are stored. So therefore, the first 1, 2, 3 value will be stored in the first attempt. That means no page fault found because we had space for storing 1, 2, 3, so no page faults. So when you go for the second attempt, so I want to store the value, next value 4. So what happens here is only 3 frames are available. All the 3 frames contains the values. Now I want to store the value 4. So I have to choose the victim to store that particular value 4 and replace that victim value. So according to this algorithm, whichever frame is allocated first will be the victim for the next allocation. So here 1 will be the first frame which is allocated. After that 2 is allocated. After that 3 is allocated. So which is the first frame here allocated? 1 is the first frame here allocated. So therefore, for storing the next value 4, 1 will be replaced with 1 is the victim which needs to be replaced and 4 will be stored in that place. And when you want to store the next reference string 1 after 4, you can say that the second page is the victim here after 1. So therefore 2 will be removed and 1 will be stored. And when you want to store the next value in the reference string 2, So what is the next value which came after 2 is 3 in the page. So therefore 3 is going to be the victim. So you have to remove the 3 and you have to store the 2. So whenever you think the page is not found, so 4, 1, 2, for that you have used the page replacement technique. So totally how many false you had? 3 false. And when the first time when you see the reference string 1, 2, 3, it is not available, only empty space is available. So therefore 1, 2, 3 is allocated here with the 3 page fault. So that totally you have 6 page fault. And what is your next value to be allocated in the reference string is 5. So now the value in the frame 3 frame is 412 only. So you check for the reference string 5, which needs to be replaced. So you can say that out of this 412, which is the first frame which came in 4. So therefore 4 reference string will be removed and 5 is stored in the page. So it is counted as another page fault. And again, what is the next value to be stored is 3. So the next arrival of page after 4 is reference string 4 is 1. So 1 will be removed and 3 is replaced. After that 2 will be removed and 4 is replaced. So totally you have 9 page faults here. So it is of 3 frames. When you go for 4 frames, the page fault rate gets increased. So therefore, it is going to be 10 page faults. So it is known that it can be identified from this first in first out is that whenever the frames increased, the page faults also increased. So therefore, this corresponding reference string can be stored better in FIFO only if it has 3 frames instead of 4 frames. And this has been given as a diagrammatic representation here. Also, another reference string has been used here. So you can see that all this reference string 7012 till 01. So we will see this example. So at the first time you have only 3 frames here. At the first time when you check for 7 inside the frame, it is not available. So it's again a one page fault. And after that 0 is checked inside the frame, 0 is not available. It's again another page fault. And 1 is also not available. So it's another page fault. And 2, which is already available. So no need for the page replacement. Do you understand? So 701 is already stored. And when you go for 2, what is the victim? 2 is not available in 701. So therefore, one of the page needs to be taken as a victim. So 7 needs to be taken as a victim because it came first. So therefore 7 needs to be taken as a victim. And similarly, when it goes for the next string 0, 0 is already available. So there is no page fault. And when you go for 3, 3 is not available. So therefore the next string which came after 2 is after 7 is going to be 0. So therefore 0 is the next victim. Replace 0 with 3. Similarly, it goes on. So all these, so totally how many page faults you had is, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you had totally for this particular reference string, if you use 3 frames, then you had 15 page faults. And what is B-Lady's anomaly is when number of frames gets increased, number of page faults decreased. But actually what happened in FIFO is number of page faults, number of frames increased, automatically page faults get increased. But here, according to B-Lady, it is opposite. So therefore, it is called as an anomaly. So this FIFO is not actually accepting or coincide with the B-Lady's content. So therefore, it's an anomaly. So what is optimal algorithm? So this is the next page replacement algorithm. First one is the first in, first out page replacement algorithm. And now we are going to see the optimal algorithm. So what is optimal algorithms is instead of taking the victim, the first page, first arrived page, you're going to replace the page that will not be used for longest period of time. So you have to see the pages already in the frame, which is not being used as a victim. So that page can be selected. So according to this four frame, when for this reference string 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So if 4 frames are used, totally it is going to have only 6 page faults. So you can see with another example for this optimal page replacement algorithm. So first 701 is stored. When it goes for 2, you can see in the previous value 701, the longest period of time, the page which is not referenced is 7, because recently 1 is referenced, and very recently 0 is also referenced, but not recently 7 is referenced. So therefore 7 will be taken as a victim and 2 will get replaced. 0, when you check for the next reference string 0, it is available, so no page fault. When it comes for 3, 3 is not there. So now when you check in the value of 201, which is the longest period of time, actually it is not used in the previous value. When you check the 201, you can say that 1 is the longest period of time which is not used. So therefore 1 will be replaced with the 3. And similarly 0, the next string is already available, so no page replacement is needed. So when you go for 4, so what is the longest period of time in 203, which is not referenced? So you can say that 0 is not referenced for the longest period of time. So therefore 0 will be taken out, and 4 is replaced accordingly in 0. So similarly, when all the reference strings has been placed in frame, so you can see the number of page faults available: 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally 9 page fault is available for the corresponding reference string. So you can say that in FIFO, when you use the same reference string, it was totally 15 page fault. And when you go for this optimal page replacement algorithm for the same reference string, the page fault is only 9. So therefore, optimal page replacement algorithm is better than the FIFO algorithm for the 3 frames usage. And the next algorithm we are going to use is least recently used algorithm, LRU algorithm. And the reference string 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5, 4 frames are used. So totally you have 8 page faults. So for what is least recently used is whichever is taken as a victim for a replacement very shortly. So least recently used value will be taken as a victim for the next changing. So you also have a counter for every page entry in this type of algorithm. So every time when a page is referenced through this entry, the clock will increase the value of the counter. So when a page needs to be changed, that is, it needs to be taken as a victim, look at the counters to determine which are to change. So look at the counters, that how many times the pages has been replaced. So whichever is the least recently used, that page can be used as the next victim. So this is the reference. The same reference string is used for the replacement using LRU. For the first time, 701 will not be available. So it is actually 3 page faults. And when you check for the next value, what is the least recently used value of 0, 1, and 7? When you check the values after the 2, you can say that least recently used is 7, because only at the last you're going to use it. So therefore 7 will be replaced by 2. 0, the next reference string is already available, so it is not a page fault. When you take the next value 3, so you can say that out of 201, after 3, you can see that 1 is referenced only after long time. So therefore, 1 can be um, used as a victim for changing the value 3 reference string. So 203. Similarly, when you go for all the replacement until 1, so you can say that 12 page faults available for this LRU page replacement for the same reference string. So for FIFO is 15, LRU is 12, and optimal is only 9. So which is better? Optimal is the better replacement algorithm. So in this LRU approximation algorithms, you have a reference bit. So each page is associated with this bit. Initially, it is 0. So when that page is referenced, then it will be set to 1. So replace the 1, which is 0. So what happens is when you check for the continuation of reference string to be replaced, you also check the bit associated with the page. You check if it is 0, you can use it for the replacement and change it to 1. When you see 1 already for that page, which means it is already referenced. So you better leave that page and go for checking for the zeros, the consecutive or the next 0 which is available after the string. So whichever is 0, again you take it as a victim page for the replacement and convert the replacement bit reference bit to 1 again. So this is how you're going to use the reference bit for the finding of the victim. So what is second chance? So second chance is you are giving second chance for the page to be acting as a victim. So it needs a reference bit and a clock replacement. So the clock will be set again to default value, and again it starts. So if page to be replaced in clock order and has reference bit equal to 1, then you have to follow the steps. So what is here is this diagrammatic representation of the second chance clock page replacement algorithm. So you have a reference bits 0, 0, 1, 1, 0, and 1, 1. So you have some pages, circular queue of pages. So the reference bit of the next victim is 1, which is arrow marked here. So in order to give a second chance, what is second chances? You convert the bit to 0 so that it cannot be used as the next victim. So 1 represents that it is very recently used as a victim. So you cannot be able to use the same page for same page as a victim again. So in order to give it a second chance, change the bit of the 1 to 0. So what happens is, again, you have to search for the next one. So when you go for searching for the next one, so it would have taken longer time because you search the next value of 0. So the 1, you can find the 1 only after 10 pages. So that means after 10 pages means uh, it is not used very recently. So therefore you are using that as a victim. But the nearest one, which means recently it has been used, so therefore you give a second chance to that page. So you leave the page after changing it the bit to 0, and when you move on to the next pages, you can see in any of the pages 1, which means this page is used for a very long time. So after a long time only we are going for checking this 1. So which means it is dead. It has been referenced for as a victim page only before a long time. So therefore you choose that page, that 1 as a victim page, and leave the first one which you find because it has been used as a used recently as a victim page. So this is the second chance what you're giving for the pages not to come as a victim, not to be taken as a victim by the memory. It sometimes you can see that it's like a cheating, but we don't have any way because the same person cannot be, or the same page cannot be a victim for a long time. So therefore, you are giving a second chance for the person which is already a victim or the page which is already a victim, and go for the next page. That is what you are doing in the second chance page replacement algorithm. And what is counting algorithm is you need a counter for each page, and LFU algorithm is least frequently used. That is smallest count, whichever page is having, you have to replace that page. MFU is maximum uh, frequency count. So based on the argument that the page with the smallest count was probably just brought in and has yet to be used. So whichever page is having the smallest count that is yet to be used, so you take the count of largest one, that is maximum frequently used. And what is priority allocation? Priority allocation is for each page, you represent a priority value. If the priority is high, that will be allocated. If the priority for a page is low, that will not be allocated. So use a proportional allocation scheme using priorities rather than size. If process PI generates a page fault, select for replacement one of its frames. Select for replacement a frame from a process with a lower priority number. That is the priority allocation. So global versus a local allocation. What is global replacement is process selects a replacement frame from the set of all frames. One process can take a frame from another. So global replacement is group of frames has been allocated. So from all the groups, any page can be taken as a victim. That is a global replacement. Local replacement is only you take one group, and inside that group, whatever page is there, you have to select as a victim only in that particular group. Then it is called as a local replacement.